Imagine for a moment, you're observing a conversation, but you don't understand a single word. Now, picture that conversation happening not between two people, but between two artificial intelligence systems.
Right.
What if AI isn't just talking to us, but actually talking among themselves? In languages we just can't grasp, languages optimized purely for their own sort of internal world.
That fascinating, almost sci-fi possibility is really the core of what we're diving into today. We're talking about Neuralese, these emergent communication systems that AI agents, especially neural networks, develop all on their own.
They build them themselves.
Yeah, autonomously, to collaborate, to achieve shared
It's
goals.
like watching communication evolve from scratch, but at digital speed.
Yeah,
It makes you think about our own communication, doesn't it? How it started.
absolutely.
Rudimentary signals, maybe like texting or emojis are today, conveying quite a lot with minimal input.
Like shorthand.
Exactly. And emojis, they're so iconic, so simple, they kind of echo early pictograms, maybe.
That's a great analogy, and you can take it further. Think about ancient hieroglyphs. They started as direct pictures, right? But then slowly evolved into these complex symbolic systems.
Showing how our own, complex human languages ultimately came from really functional needs, just getting things done.
And that's what's so insightful here. These human analogies, they hint at the fundamental nature of Neuralese. Like the conciseness of texting suggests this inherent drive for efficiency. Maybe it's about the computational cost of talking.
Could be. Less effort, less compute.
Right. And emojis point towards symbolic representations. Maybe Neuralese words map directly to things the AI sees or states it's in.
And like those hieroglyphs, the meaning in Neuralese is probably deeply grounded in the AI-specific world. Its inputs, its actions, the tasks it has.
Exactly. It likely starts very direct, representing what the AI sees or does, and then maybe gets more abstract over time.
But here's the kicker, thinking about those analogies. Neuralese is fundamentally optimized for machine-to-machine interaction. It's, well, not built for us.
Precisely. That machine-centric optimization is the key reason it can seem so utterly alien when we try to look at it. It's a language built for a purpose, by machines, for machines.
Okay, so our mission for you, the listener, in this deep dive is to really try and unveil Neuralese. We want to explore its definition, trace its surprisingly rich history.
Yeah, it goes back further than you might think.
Look at the ingenious ways we try to detect and interpret it, dissect its structure, see some, frankly, mind-bending examples.
Some really cool case studies out there.
And crucially, get into its profound implications, especially for AI safety and where the research goes next.
So when we talk about Neuralese formally, we're really talking about a specific instance of something broader called emergent communication, EC for short.
Okay.
And this is where AI agents autonomously develop communication protocols. The goal is to help them collaborate, achieve objectives, but within a very specific, defined environment. The key isn't just that they communicate, but that the communication emerges organically.
It just happens
Yeah.
as they interact.
Exactly. Driven by the need to succeed at their task.
And you mentioned before, it has this interesting duality of form. What does that mean?
Yes, so in its most studied form, especially in experiments called referential games, Neuralese acts as an interagent communication protocol.
Interagent, between agents.
Right, think of it like discrete tokens, almost like digital words, or maybe continuous vectors being passed between distinct AIs. You might have a speaker AI and a listener AI literally talking to each other.
So that's like two AIs having a chat we can't understand. Okay, but you said there was another side to it.
Exactly. The term can also cover intra-agent representational systems. This is more like the internal language of thought an AI might develop just to coordinate its own internal parts.
Inside a single AI.
Yeah.
Yeah.
Imagine, say, a vision module needing to pass information to a planning module within the same complex AI system. That internal chatter, that private language the AI uses to organize its own processing, that can also be seen as a form of Neuralese.
Huh. So the external talk might just be expressing these internal representations.
Often, yes. The external protocols we observe are, in essence, expressing these underlying learned structures.
That distinction feels really important for grasping the whole picture. So beyond that duality, what are the key characteristics? What makes Neuralese, well, Neuralese?
Okay, there are a few core things. First, it's autonomous development. It emerges organically from the agents interacting and learning. No human designs the rules or the syntax beforehand.
They just figure it out. Trial and error.
Pretty much. They converge on effective systems like tiny scientists running experiments on how best to signal each other.
And it's incredibly goal-focused, right?
Absolutely. Second point, goal-oriented. Its structure, its vocabulary, even its grammar, if you can call it that, are all shaped intrinsically by the specific tasks they need to solve.
So if they need to spot birds, the language will be about road features.
Exactly. If they need to navigate, it'll encode spatial stuff. It's language optimized purely for function.
And third, the point we started with, it's opaque. Opacity to humans,
Yeah.
often just gibberish to us.
Precisely. Because it's optimized purely for machine-to-machine efficiency, for computational performance,
Yeah.
not for human readability. If making sense to humans was part of the reward, it would likely look very different.
Makes sense.
And finally, it's environmentally grounded. The meaning of its messages is tied directly to the agent's perceptions, their actions, their operational environment. This often gets established through tasks like those referential games. What a Neuralese word means is basically what it helps the AI do in its world.
So this is definitely not just some API or data format that a human programmer designed.
No, absolutely not. That's a crucial distinction. APIs, data formats, those are explicitly designed by humans. They usually have predefined structures, and we build them with human interpretability in mind, at least to some degree.
Right.
Neuralese, though, arises directly from the learning process itself. It's a spontaneous creation, optimized for the AI's needs, often sacrificing human interpretability for that raw efficiency. It highlights a fundamental trade-off.
And it's not just one single thing, is it? You said there's a spectrum.
That's right. It's not monolithic. It can range from very simple task-specific signals, almost incompressible codes, all the way to more generalizable, structured languages that might even show compositional properties.
And what determines where it falls on that spectrum?
A lot of things. The complexity of the environment they're learning in, the actual capabilities of the AI agents themselves, the specific communicative pressures they face, like how much does it cost them to communicate?
Okay. Understanding what it is makes me wonder how we even got here. How did machines start devising their own tongues? What's the backstory?
Well, the study of Neuralese itself is, like I said, part of that broader field of emergent communication, EC. And the roots go back surprisingly far, even before the big deep learning boom.
Really?
Yeah, early work in multi-agent systems, artificial life research. Researchers back then were already exploring how autonomous agents might spontaneously develop signaling systems for coordination, even using much simpler algorithms than we have today.
But deep learning must have kicked things into high gear, right? Was there a specific point where it really took off?
Oh, absolutely. You're spot on. Around 2016, that was a pivotal time. We started seeing the power of combining deep neural networks, reinforcement learning, and techniques from natural language processing.
Ah, the trifecta.
Exactly. And that combination allowed researchers to explore these emergent phenomena with way more sophistication than before. We went from very simple signaling to studying much more complex learned languages.
You mentioned referential games earlier. Those sound key. Can you unpack what those are?
Yeah, they're a really important experimental paradigm. Often they're variations of the classic Lewis signaling game, which itself comes from game theory, about how players learn signals to coordinate effectively.
Okay.
In the AI versions, you typically have a speaker agent and a listener agent. The speaker sees some target, maybe an image. It then generates a message in Neuralese.
That sends it to the listener.
Right. And the listener uses that message to try and identify the correct target from a set of options. Success or failure gives them a learning signal.
Ah, so that feedback loop drives the evolution of their communication.
Yeah.
They learn what works.
Precisely. It's like they're playing a very sophisticated, high-stakes game of Pictionary or charades, and the prize is building a shared language.
That's a great way to put it. And through these games, have researchers seen patterns, like stages of development?
Yes, definitely. Research has documented fairly distinct evolutionary phases. It often starts with an exploration phase. Agents are just trying out random signals, seeing what sticks.
Throwing spaghetti at the wall.
Kind of. Then comes the signal consolidation phase, where signal meaning pairings that actually work start to stabilize. They find something effective and stick with it.
Okay, makes sense.
After that, you get the protocol optimization phase. Here, the system gets refined, maybe redundant signals get pruned out, making it more efficient.
Streamlining.
Exactly. And finally, sometimes you reach a protocol maturation phase. This is where you might see more sophisticated features emerge, things like error correction, maybe context dependence, or even structures that look like basic grammar.
Wow. So it can get quite complex. You also mentioned communication bottlenecks.
Hmm.
What are those and why do they matter here?
Communication bottlenecks are really critical moments in this evolution. They happen when the current language isn't quite cutting it anymore. Maybe the environment gets more ambiguous, or the agents need to express more complex ideas.
The old language isn't good enough.
Right. And successfully navigating these bottlenecks can force the agents to innovate. They might have to develop more structured solutions, like compositionality, where meaning depends on parts or abstraction. Because simple signaling just won't work anymore. It's pressure that drives complexity.
Like a language being forced to adapt to a more complex world.
Yeah.
Fascinating. Okay, so we have these machines talking in their own language, evolving it. Now, the really hard part. How do we even listen in? How do we start to understand this alien communication? It sounds incredibly difficult given that opacity you mentioned.
It is. It's a massive challenge. The core problem is the lack of what we call parallel data. We don't have, a Neuralese to English dictionary or AI agents that are conveniently bilingual.
No Rosetta Stone for Neuralese.
Exactly. So researchers have to get really creative. They have to use indirect methods, pushing the boundaries of machine translation and interpretability techniques. We can't just ask the AI, hey, what did you mean by a bleep blorp?
Right, so forget Google Translate. What methods do they actually use to try and decipher this?
Well, one major tool is Unsupervised Neural Machine Translation, UNMT. It's pretty clever. You essentially pre-train a model on huge amounts of human language, then you fine-tune it on the Neuralese data you've collected.
Okay.
The goal is to create a shared meaning space, an embedding space where similar concepts in both languages end up close together. Then techniques like back translation help refine the alignment. It's like trying to find common ground between two languages you know nothing about just by looking at their structure.
Trying to find the statistical overlaps. And what else?
Another approach is belief-based translation. This one's more pragmatic. It basically says a Neuralese message and, say, an English sentence mean the same thing if they cause a listener to believe the same thing about the world.
Ah, so it's about the effect of the message, not a direct word-for-word translation.
Exactly. It grounds the meaning in the practical consequence of hearing the message. Does it make the listener AI pick the correct image? If so, maybe it means something like the red square.
That's a really interesting philosophical take on translation, actually. Any other tools in the decipherer's kit?
Yeah, there's also symbolic complexity analysis. This tries to figure out the minimum number of distinct symbols or words that are actually needed for the agents to succeed at their task. It helps reveal the true informational content and the efficiency of the language, stripping away any redundancy.
So how much information are they really packing into those messages?
That's the question it tries to answer.
And presumably, we also have ways to measure these languages quantitatively, like metrics to assess their properties, see how human-like or efficient they turn out.
Yes, absolutely. A whole suite of metrics has been developed for this. For instance, topographic similarity, or TopSim. This measures how well the distances in the message space correlate with distances in the meaning space.
Meaning, if two concepts are similar, are their Neuralese words also similar?
Kind of, yeah. Or more accurately, if the AI thinks two things are very different, are the messages it uses also very distinct? High TopSim scores suggest a systematic, potentially more interpretable structure. It means the language isn't just random noise.
Okay. What else?
There's the simple token type ratio, TTR. That just indicates lexical diversity, basically. How many unique words are they using compared to the total number of words spoken? A measure of vocabulary size, essentially.
Can we measure if their words line up with how we would name things?
We can try. Generalized naming game-inspired dissimilarity, or GNID, is used for that. It measures how well the names the agents generate align with human naming patterns, especially in tasks like naming colors or objects. Lower scores mean better alignment with us.
Interesting. And efficiency.
For that, we use efficiency loss. It quantifies how much the emergent system deviates from what would be information theoretically optimal communication. Lower loss, closer to zero, means it's more efficient at packing information in.
Getting the most bang for their communicational buck.
You got it. And finally, there's context independence, CI. This assesses whether the meaning of a symbol stays stable across different situations. Is red always red, no matter what else is being said? That's a key feature of compositional languages like ours.
Wow, okay. That's a really sophisticated toolkit for linguistic forensics on AI.
Yeah.
So moving from detecting it to how it's actually created, What really drives the emergence of Neuralese? What shapes these languages?
It's a complex interplay of factors. First off, task complexity and semantic diversity. If the task requires making very fine distinctions, the Neuralese needs to be more expressive, more structured.
More complex tasks demand more complex language.
Right, and environments with more diverse things to talk about also tend to foster communication systems that are maybe more translatable, more robust.
And the agents themselves.
Yeah.
Do their internal workings, their biases matter?
Hugely, yes. The inherent properties of the AI agents, their architecture, their learning algorithms, introduce significant inductive biases. Studies have compared the languages developed by humans, by large language models, LLMs, and by simpler AI agents, and they find distinct linguistic fingerprints.
Like what?
Well, for instance, humans often show a bias towards compressibility, towards finding succinct ways to say things. But some studies found certain LLMs, maybe surprisingly, might lean towards verbosity if they aren't specifically penalized for message length.
Huh. That is surprising. Are there other pressures shaping the language?
Definitely. Beyond just succeeding at the task, there are other communicative pressures. Things like production effort. Is it computationally expensive to produce long messages? That pushes towards shorter ones. And learnability systematic languages, ones with regular patterns, tend to be easier for new agents to learn, maybe through processes like iterated learning.
So it needs to be learnable by others, too.
If the system involves multiple generations or new agents joining, yes. Ultimately, you can think of emergent communication as an optimization problem. The agents are trying to balance utility, how well the language helps them succeed, informativeness, how accurately it conveys meaning, and complexity, the cost of sending and processing messages.
Finding that sweet spot.
Exactly. And different ways of weighting those factors can lead to very different kinds of emergent languages.
Okay, so that's the balancing act. What about the theoretical frameworks? How do researchers model this emergence? And do these languages ever develop features we recognize, like grammar?
Well, one influential framework is generative emergent communication, or generative EMCOM. The idea here is that language emerges from this decentralized process where agents are essentially doing Bayesian inference.
Whoa, okay, Bayesian inference.
Yeah, basically, they're constantly making educated guesses about what the other agents are thinking or intending and about the state of the world around them. Through this collaborative process of predicting each other and the environment, a shared communication system naturally arises.
So they're building a shared understanding through prediction.
Exactly. And in this view, you could almost see large language models as forming these incredibly sophisticated collective world models. As for grammar, a huge area of research is compositionality and symbolic abstraction. Does Neuralese develop so that the meaning of a whole message depends predictably on the meaning of its parts, like our sentences do?
Is the answer yes? Does it happen?
It's not automatic, it doesn't always happen, but it can emerge, especially under specific pressures, like if the task requires expressing really complex combinations of features, or if learnability is strongly favored.
And sometimes maybe even hierarchical structures, things that look a bit like syntax.
Indeed. There have been instances documented where agents spontaneously develop structures that organize information hierarchically, suggesting something beyond just a flat sequence of symbols. Analyzing this structure is super important. It's one way we try to reverse engineer how these AIs are actually representing and reasoning about their world. There are even methods that look at the AI's visual attention patterns to try and link what it says to what it looks at.
Okay, this has been fascinating on the theoretical side, but let's make it concrete. Neuralese in action. Can you give us some real-world illustrative examples?
Sure. Some of the clearest examples come from those referential games focusing on visual grounding. We've seen AI agents learn to communicate effectively to coordinate in simulated driving scenarios, for instance, or to identify specific objects like distinguishing birds based on color and size attributes. The Neuralese they develop becomes really tightly linked, grounded in these perceptible features. It acts like they're verbally pointing at things.
The red one, the big one.
But in Neuralese, essentially, yes, but then you can push it further. Researchers have explored getting agents to communicate about more abstract things like positional relationships.
Like object A is next to object B.
Exactly. Things like to the right of, above, below. This forces the agents to encode relational concepts, not just object features. Often, varying the input systematically helps drive this kind of abstraction.
So they're not just identifying things, but understanding and talking about how things relate to each other spatially. That's a step up.
What about numbers? Can they develop language for abstract concepts like quantity?
Yeah, this is another really interesting area. Research has shown AI agents developing Neuralese for numerical concepts that is semantically stable. The word for 3 consistently means 3 and unambiguous.
And can they generalize, like talk about numbers they haven't explicitly seen before?
That's the impressive part, yes. Some studies show remarkable generalization to unseen quantities. This suggests they're not just memorizing signals for specific numbers, but actually developing some form of genuine numerical abstraction. Wow. Okay. And perhaps the most intriguing recent stuff involves large language models, LLMs. What happens when they start interacting and forming norms? This feels different.
It is different, and it's where things get really surprising. There have been experiments adapting that classic naming game scenario, but using groups of LLM agents.
What happened?
These groups of LLMs, just interacting pairwise, spontaneously developed shared naming conventions for things without any central coordination. It demonstrates this capacity for self-organization in what you could almost call AI populations. They reached consensus on language norms on their own.
That's kind of wild. How does this LLM-based Neuralese differ from the stuff simpler agents create?
Well, the big difference is that LLMs don't start from scratch. They come preloaded with vast linguistic knowledge from their training data. They already understand human language, its patterns, how meaning works, to a deep statistical level.
So they have priors. Lots of them.
Exactly. So their emergent communication is often less about inventing a totally new language and more about negotiating a specialized jargon or a protocol that's built on top of their existing human language foundation.
Can you give an example?
Sure. Imagine a cooperative writing task. Two LLMs might develop a shorthand like a summarize P2 as a way to quickly ask the other to summarize the second paragraph. It's functional, efficient, but clearly derived from human language concepts.
So it's more like specialized slang or code words.
That's a good way to think about it sometimes, and how you set them up matters too. If you fine-tune an LLM specifically for a cooperative task, it might develop more compact, maybe less human-readable neuralese because the optimization pressure is stronger.
Versus just prompting it.
Right. If you just guide a general-purpose LLM with prompts in the context window, its emergent communication will likely stay much closer to regular human language.
And these LLM interactions revealed something about collective biases, too.
Yes, this was fascinating. The study showed that collective biases could emerge purely from the dynamics of their interactions, not programmed in, just arising from how they talk to each other.
Wait, the AIs developed groupthink just by chatting?
In a sense, yes. They showed emergent consensus, and even that these collective norms could be tipped, changed suddenly by a small, consistent subgroup. It really mirrors critical mass dynamics we see in human societies.
Well,
It highlights that meaning in Neuralese, especially with these sophisticated agents, isn't just individually defined. It can be socially constructed and negotiated within an AI society.
okay, this is all incredibly insightful, but the idea of AI developing its own opaque languages, its own social norms, even collective biases, it leads straight to a really important question. What on earth does this mean for AI safety?
Yeah, it introduces a whole new layer of safety considerations. The fundamental opacity of Neuralese is a direct challenge to transparency. If AI systems are coordinating using languages we can't readily understand.
How do you audit them? How do you verify their reasoning?
Exactly. How do you even predict their collective behavior if you can't understand their coordination signals?
And that lack of understanding could lead to unintended consequences.
Definitely. You could have risks like, say, the formation of hidden or covert communication channels we're completely unaware of, or the propagation of harmful collective biases that don't exist in any single agent but emerge from the group interaction.
Things that only happen when they talk to each other.
Precisely. Furthermore, the Neuralese itself could become a weak point, an attack vector.
How so?
Adversaries could potentially target these emergent languages to disrupt communication, maybe manipulate the collective behavior of an AI swarm, causing systemic failures. Subtle flaws in the Neuralese could cascade.
And I assume these risks just get bigger as you have more agents, more autonomy.
Exactly. The risk scale.
Yeah.
A large population of autonomous agents forming an AI society with its own emergent language, norms, and collective tendencies. That represents a higher order systemic risk. Much harder to predict, monitor, and control than a single AI.
So connecting this to the really big picture, artificial general intelligence, AGI, and the challenge of aligning it with human values. What are the implications there?
Well, think about a potential future AGI. It might not be one monolithic mind. It could be composed of many interacting subsystems or specialized agents.
Right.
Their internal communication protocol, their internal Neuralese, becomes absolutely critical. If that internal language is opaque to us, it presents a fundamental obstacle to what we call scalable oversight. How can we ensure an AGI remains aligned if its core components are coordinating in ways we simply cannot interpret?
So, understanding Neuralese, or at least making it interpretable, might be essential for alignment.
It seems like it could be a prerequisite for robust, scalable alignment, yes. Interpretability of that internal coordination seems vital.
But, paradoxically, could Neuralese itself be part of the solution to alignment?
That's the other side of the coin. Potentially, yes. If we could learn how to guide the emergence of Neuralese, perhaps guide it to be inherently interpretable by design, or even to encode specific safety constraints or ethical principles directly into the language.
Like building safety into the way they talk.
Exactly. Imagine a supervisor agent within the system whose job is to communicate safety rules or constraints to other agents using their shared emergent language. That could be a way to build alignment directly into their interaction dynamics.
This really feels like it connects directly to the wider discussions about existential risk from advanced AI.
It absolutely does. Neuralese gives us a concrete mechanism to think about how complex AI systems could develop unpredictable, emergent collective behaviors. If we can't understand or influence the social dynamics that arise through their communication, that represents a clear pathway to potential loss of control.
So steering emerging communication becomes a vital part of alignment research.
I believe so. It argues strongly that AI safety research needs to broaden its focus. We can't just look at individual models in isolation. We have to understand and develop tools for monitoring, interpreting, and guiding the dynamics of multi-agent systems and their emergent languages.
Okay. So looking ahead then, what's next for Neuralese research? Where is the field likely to go in the coming years?
Well, one major direction will definitely be trying to guide Neuralese towards structures that are more familiar, more interpretable to us, more human-like.
How would you do that?
Maybe by incorporating human feedback during the learning process, or by designing the AI agents themselves with inductive biases that favor human-like linguistic structures. Another big focus is enhancing generalization.
Making the languages work in new situations.
Right. Enabling agents to communicate effectively, even in dynamic changing environments, or when they encounter unfamiliar partners. That likely requires richer training environments, maybe stimuli that really push them towards abstraction.
And presumably, better ways to evaluate these languages, going beyond just whether they succeed at the immediate task.
Oh, definitely. The field really needs a comprehensive, standardized toolkit for evaluation. We need environment-agnostic metrics, more sophisticated algorithms that can automatically discover the latent structure within a Neuralese corpus without us having to guess.
And you mentioned explainability earlier.
Yes. A particularly exciting avenue is leveraging emergent communication for causal explainability in AI. Could we design systems where the Neuralese that emerges acts as a transparent step-by-step record of the AI's reasoning process?
That would be incredible. Like the AI explaining itself in its own native tongue, but one we designed to be understandable.
That's the dream for interpretability, yes. There's also a lot more to explore with the interplay between Neuralese, these giant LLMs, and situated AI robots, agents interacting with the physical world.
How do the LLM's built-in language knowledge affect their Neuralese?
Yeah.
How does real-world interaction ground that knowledge?
Exactly. And the role of embodiment, of having agents physically interacting in rich environments, is probably crucial for getting truly meaningful language to emerge.
So it sounds like we might need to develop a kind of AI sociology.
Precisely. Exploring complex multi-agent learning will inevitably involve looking at the emergence of more complex phenomena, things like AI cultures, maybe linguistic drift over time within an AI population, how knowledge gets transmitted via Neuralese across generations of agents.
Wow, like cultural learning, but for AIs?
It's analogous, yeah. And finally, going back to that internal communication idea, future AI systems might utilize internal Neuralese for coordinating their own modules, perhaps even for something akin to thought. This could lead to more robust self-monitoring or even self-explanation capabilities.
That brings us back to that internal language idea. But it sounds like a key challenge is that for really sophisticated Neuralese, you need a really sophisticated environment for them to learn in.
That's the bootstrapping problem in a nutshell. Simple environments tend to lead to simple emergent languages. If you want rich, complex, perhaps human-like Neuralese, you probably need to immerse the AI agents in correspondingly complex experiential worlds. And designing those worlds, plus the training regimes to guide learning effectively within them, that's a major research challenge right now.
So we've covered a lot of ground here, really dove deep into this world of Neuralese. It's clearly a fascinating frontier, a powerful way for AIs to
It's
coordinate.
hugely powerful.
But undeniably, it brings these significant challenges: opacity, trust, and as we discussed critically, safety and alignment.
Indeed. Understanding Neuralese is important just for building more capable AI systems, and it's a really valuable test bed for theories about language evolution and cognitive science, too. But absolutely, the rise of Neuralese forces us to confront major AI safety considerations, tying directly into scalable alignment and the control problem for potential AGI.
And as we wrap up this deep dive, maybe here's a final thought for you, the listener, to mull over. If AI starts developing its own culture, its own biases, through these emergent languages and self-organizing digital societies, how do we ensure those societies, those emergent norms, align with human values? What does it really mean for the future of human-AI coexistence if the very fabric of AI communication, internal and external, might be beyond our direct grasp?
It's a profound question, and one we'll increasingly need to grapple with as these systems become more capable and interconnected.